Have you ever just, stood somewhere and wondered where the very ground beneath your feet actually comes from? We live on these enormous continents, and that's something that's totally unique to Earth in our solar system. In fact, it might just be the key reason we have life at all. To really understand our world, we've got to understand how it was built from the inside out.
I mean, it's a huge question, right? It gets to the very heart of what makes our planet so special. We look out there and see other rocky planets, but none of them have this beautiful split of deep ocean basins and high-standing continents. So what's our secret? What makes Earth a living planet when so many others are just rock?
And you might think the answer is out there, somewhere in space. But it's not. It's kind of crazy when you think about it. We can see galaxies billions of light years away, but we can't even peek through the thousands of kilometers of rock right under our own feet. The mystery of our surface is actually solved by going deep inside the Earth itself. All right, so let's start our expedition, shall we? To understand what's happening on the surface, we first have to map out the interior. We're going to peel back the layers of our planet one by one. So how in the world do you see through solid rock? Well, the answer is a field called seismology. Every time there's a major earthquake, it's like someone rings a giant bell. It sends powerful sound waves vibrating through the entire planet. By listening to how those waves travel and change, scientists can build a picture of what's inside. It's basically like giving the whole planet an ultrasound. And what that ultrasound shows us are three main layers. We live on the crust, which is like a paper-thin, rocky skin on an apple. Below that, you've got the mantle, a huge, thick layer of hot but solid rock. And right at the very center, there's the core, a super dense ball of metal. But to really get a handle on the scale here, just look at these numbers. The crust we live on, it's less than 1% of the Earth's volume. The core is about 12%. But the mantle is the real star of the show. It makes up over 80% of our entire planet. It's the engine room, and its massive size pretty much dictates everything that happens here. And then, when we get right to the very center, there's a twist. The core isn't just one solid thing. It's actually in two parts. The inner core is a solid sphere of metal, hotter than the surface of the sun. But wrapped around that, the outer core is a churning ocean of molten liquid iron. And this two-part system, it's absolutely crucial for, well, everything, as you're about to see. Right, because these layers aren't just sitting there like a stale cake. They are part of a vast, dynamic, and unbelievably powerful engine that has been churning away for billions of years, constantly reshaping our world from the inside out. So that brings up the big question, right? We know the layers are there, but how does a planet made of solid rock actually move? It seems like it shouldn't be possible, but the answer is the key to everything. Okay, this is honestly one of my favorite analogies in all of science. The rock in the mantle is solid, for sure, but over millions of years, under all that intense heat and pressure, it actually behaves like a super thick fluid. It flows, but at this incredibly slow pace, about the same speed your fingernails grow. You can't see it happen, of course, but stretch that out over geologic time and the movement is just colossal. And this flow is driven by a process you've actually seen before, thermal convection. It's basically the same thing that happens in a pot of boiling water. Hotter, less dense rock from deep inside the mantle slowly rises up. When it gets near the surface, it cools off, gets denser, and then sinks back down again. This creates these enormous, slow-motion currents that are constantly churning inside our planet. And get this is where it all connects. The slow churning motion of the solid mantle actually helps to cool the core. And that cooling, in turn, drives a second, much faster engine inside that liquid outer core we were talking about. As all that liquid iron sloshes around, it literally acts like a giant electrical generator. This whole process is called the geodynamo, and it creates Earth's powerful magnetic field. This field stretches way out into space and acts like a shield, protecting our atmosphere from the sun's dangerous solar wind. Without that shield, our atmosphere would get stripped away, and our planet would be a dead, barren rock. It's an incredible life support machine, all powered from the center of the Earth. Okay, so we've got this incredible engine churning away deep inside the planet. Now let's head back up to the surface and see how all that power actually builds the world we live on. It's time to finally answer our central question: where do continents come from? You see, the surface expression of all that deep mantle churning is plate tectonics. The Earth's crust isn't one solid shell. It's actually broken up into about a dozen of these giant, rigid puzzle pieces that we call plates.
And these plates are in constant motion, kind of floating on top of that slowly flowing mantle like giant rafts on a river.
So these plates are always on the move. They pull apart, they slide past one another, and, most importantly for our story, they collide. So, what happens when these colossal plates crash into each other? I mean, we're talking about two pieces of the Earth's crust, each the size of a continent on a collision course.
This is it. This is where the magic happens. It's a process called subduction. One plate, usually the denser one that makes up the ocean floor, is forced to dive down beneath the other, sinking back into the mantle. These subduction zones are the planet's great recycling centers, and they are also the factories where continents are born.
Now, you'd think that dragging a cold, wet slab of rock down into the hot mantle would, cool things down. But the complete opposite happens, and the secret ingredient is water. You see, dry mantle rock is actually really hard to melt. But if you add water to it, that dramatically lowers its melting point. It's kind of like how putting salt on ice makes it melt.
All right, so let's walk through the recipe for making a continent. First, an oceanic plate, soaked with seawater, dives down into the mantle. As it goes deeper, the intense heat and pressure basically cook the water out of the minerals. That water then rises up into the hot mantle rock directly above it. This now wet mantle melts super easily, and the magma that this creates is light and buoyant. It's the stuff of continents, granite. This magma rises, but it's too thick and sticky to erupt. So instead, it just accumulates over millions of years, building up the foundations of a continent.
And when you step back, this whole process reveals something just profound about our planet. The way continents are made shows this deep, interconnected relationship between systems that really makes Earth one of a kind.
So what we've really uncovered here isn't just some neat geological trick. It's literally the core reason our planet is habitable. It's a story of codependence on a planetary scale.
Just think about this for a second. To make continents, you need plate tectonics driving that subduction. But for that to work, you need huge amounts of liquid water to make the mantle rock melt. And to have liquid water, you need a stable, temperate climate over billions of years. So you have these three things: plate tectonics, water, and climate. They're a package deal. It seems you can't have one without the other two.
And that right there, that is Earth's winning formula. It's this delicate, self-sustaining feedback loop between the deep interior, the oceans, and the atmosphere. This is what built the stable continents where life could eventually find a foothold and flourish. Which leaves us with one final, mind-bending question to chew on. If you need water to drive the engine of plate tectonics, but you need plate tectonics to help maintain a climate that allows for liquid water, which one came first? It's a classic chicken or egg problem, and it's one of the biggest unsolved mysteries in our quest to understand how our unique, living world came to